what we will look at today is the third component of the model human processor, the MHA model, and we will look at the motor skills part. Okay, why are we doing all this? Again, we are studying the psychology of the human being. We studied perceptual psychology first, followed by cognitive psychology, and finally motor psychology, if you like, to understand how a human reacts to an event in an interface, and consequently how can we design an interface to be more suitable to a human being. So we started by perception because any change that happens in an interface, the user will notice using his eyes or his ears if there is sound accompanied, and so on. So we need to understand perception, and consequently we came up with rules to enhance our design activity in an interface based on what we have learned from perceptual psychology. And we did a similar exercise last lecture with cognitive psychology. Now we come to the motor processing. Now why they are organized this way, sensory, cognition, motor? Because this is how you react to an interface. You see it, you think of it, and then you react physically by either pressing a button or moving a mouse. So let's go to the motor part. What are we going to study from motor psychology? We're going to study the motor processor, a certain kind of storage in our brain called the kinesthetic store, and we will see some interesting laws. So let's start by the motor processor. So you have a processor in your brain, believe it or not, responsible for your movement. This actually processor, you know where it is? I hope you can actually immediately recognize what am I talking about. It's actually in the central sulcus, the motor cortex. Okay. Now, so we already kind of talked about it before. We said that if you would like to move any muscle, you are thinking of the movement in the frontal lobe, but the movement itself is initiated by a signal that is emitted from the motor cortex, which goes through your spinal cord and finally reaches your muscle through the central nervous system. Now, this is the new stuff now. What is the new stuff? The first thing you need to understand is that we are not jellyfish. We are not super smooth creatures that move fluidly in an environment. In fact, our motion is very jiggery, and it involves a lot of corrections. Now, the reason why it is jiggery, because the motor processor takes time to compute the next movement, and that takes about 70 milliseconds. So between the last movement and the next movement, there is 70 milliseconds of processing happening in the motor processor. Which one? Depending on which organ you are actually moving. We said we have centers in our motor cortex for every one of the muscles we move consciously and also subconsciously. So any movement requires some computations, that is about 70 milliseconds. What happens between one movement and another is that your processor is adjusting the instructions it is sending on the nerve based on the feedback it is getting from the various organs that it could use to monitor the result of the previous movement. In other words, if I say I would like to move from where I'm sitting now towards the door of my office, what happens is I reorient my body towards the door and then I start moving. Immediately, my brain is calculating what is actually the reaction to my movement. Am I going towards my target or not? And since we're not, super accurate machines, our bodies, I will deviate a little bit from the target, even by millimeters or centimeters, depending on the context here. So I will go towards the target, but not exactly towards the target. My brain will realize that, and it will send instruction to the motor cortex. All this is happening subconsciously, you're not aware of it, to readjust a little bit so that when I reach the door, my hand will be on the top of the door handle so I can open the door handle. Okay? We describe this type of movement as micro movements. and they are discrete in the sense that one comes and then finishes, and then the other one starts and then finishes, and then the next one starts and then finishes, and it goes like this. Okay, so all our movements for all body parts, whether you're walking, you're running, you're swimming, you're flying in air, it's basically what we call discrete micro movements. Corrections are happening all the time. You're not aware of it at all. It's completely subconscious to you, because if you were conscious about it, you would go crazy, because you will realize that every time you move, you're actually not going exactly where you want to go, and you will start thinking about the movement and you will try to correct it. But it is happening all the time without us actually being aware of it. Okay? Now, so this is the first interesting piece of information that you need to understand about our body and how we move. Now here is the second piece of information, which even is even more interesting than the previous one. So we have a certain part in our memory that is labeled the kinesthetic store. What it does, it stores motor movement instructions. Okay? It stores the instructions that were sent from the frontal lobe to the motor cortex to move a muscle. And this is actually one of the things that make us quite a design in terms of human creatures. The thing is, this motor storage, motor instruction storage, which is often referred to as in the literature as kinesthetic store, it is actually not just a dump of instructions. The instructions are being inspected all the time for accuracy, and are being enhanced all the time, which means the instructions are being modified to be better in our motor skills. This is why when you look at someone who has just learned how to drive, they will look like they are doing a physical tense movements while driving a car. So you find them putting their two hands on the wheel drive, and the movement is very amplituded, in the sense that they would go suddenly to the right and then suddenly to the left. Okay, what's happening is they don't have fine motor control on the steering wheel. The reason why they don't is because the instructions in their brain is still very crude. Okay, they know how to turn right, but they don't have fine control. You see the same thing in people who learn racket games, whether it's tennis or squash or table tennis. When they start playing, they look very funny. The ball will be going towards them, and they attempt to hit the ball and they miss the ball. And they keep doing that for a while, and then suddenly they start getting the ball correct. And then suddenly they become more proficient and hitting the ball and sending it to the location they would like to send it to. What's actually happening is that, or what motor psychologists have discovered, is that in our brain we have like a machine learning algorithm that keeps computing probabilities of getting it right versus getting it wrong. And as we keep doing the movement, the probabilities and the adjustments get better and better. So the adjustment gets better, which means the probability gets better, and there is a feedback process that happens. So we gradually enhance our movements by monitoring our failures and our lack of good performance, and sending that feedback subconsciously to the brain, which recomputes the values that it has sent to initiate the muscle movement in a slightly different direction, or with a slightly different amplitude, so you hit the ball right or you control the steering wheel correctly. Okay? And this is also the reason why, if you play a racket game and then you stop playing for many years, okay, and then you come back, you notice that you can still hit the ball correctly. You're not starting from scratch. You're not starting from level 0. You're actually quite competent in the game, even though you might not have played for like 10 years. And the thing is, what is happening is you activate the area in your brain that is using that has the program for controlling the racket and playing this specific racket game, and you just exercise, using that program. Okay, so you use old stored information. Okay. Now, This is also the reason why, if you look at someone who is quite old, when they drive cars, they get really, really tense, and the movements are not fluid at all. This is again a lack in the motor skills associated with the muscles that is required to do the movements. The program might still be there. If someone has been driving for 40 years, they have the instructions actually to drive. But the problem now that the muscles have aged, so they don't respond correctly to the signals sent from the kinesthetic store. But once that person health gets a boost, perhaps using multivitamins or any kind of supplement, you find that they go back to a better driving style, or a better being a better player in the racket sport. Okay, so kinesthetic store is extremely important. Now let me tell you what HCI designers have made out of kinesthetic store. This is one example. I would like you to watch the video to get the full picture. This is a menu design where the menu is not displayed. It's called the marking menus. What the user do is learn the path they travel through with the mouse to invoke a specific menu item. For example, if you would like to go from tools and select the entry beneath the word wrench, so you go right a certain distance and then you go down a certain distance. If you keep repeating this movement, it's almost like playing a racket game. You master the movement and it gets stored in your kinesthetic store. So this kind of menu is actually useful for someone who uses the same program over and over again in their daily work. For example, a graphics designer who's using Adobe Photoshop or Adobe Illustrator would be sitting for hours and hours every day doing the same stuff, invoking the same menu items. Okay? Now, if actually Adobe Photoshop or Illustrator or such a product supports marking menus, by just moving the mouse in with the right direction and in the right sequence, a menu could get invoked. Okay? So you don't actually have to display the menu. And in fact, the really interesting part here is that different users would make the same movement but with different velocities and amplitudes, but they will all reproduce the same shape, just on a different scale and with a different speed. And if the software can detect that, you don't even need to display the menu. Okay, it becomes like a gesture. If you go right and then left, that's one thing. If you go right and then bottom, that's another thing. If you go right for some distance and then bottom for another distance that is known to you, again, you're trained motor-wise to actually do those distances, then or maintain the proportions between those distances, then we will know which menu item you are actually interested in. And you can see the video, and it's well explained. Okay, the reason why this works in the first place is because we have a kinesthetic store. We store the motor instructions, so you don't actually have to worry about the user not knowing how to do this. Obviously, the first few times they do it, they will not be able to do it, but later on they memorize it, just like memorizing how you can play table tennis, for example, or how you can drive a car. Now let me tell you about a related law that is applicable only in the case of motor movements. Now the law is called Power Law of Practice, as the title says, and it calculates for you the average time that you will do an nth trial of some motor action. So that action could be, for example, you moving your hand from the steering wheel, holding the gear shift to change the gears of the car, or you extending your arm to open a door. So it has to be a motor movement. The formula is like this. N is the nth trial you're interested in, the time of the execution of the nth trial. T1 is the time it takes you to do this action for the first time ever. N again is the trial you're interested in, and A is some constant that is experimentally computed. By the way, this is the second time I talk about an experimentally computed constant, and we will see shortly in this lecture today the way of doing that. Plus C, which is another constant. Now, if you know A, you know C, you will do an experiment to actually measure T1, which is the first time you do this specific movement we're interested in, and then you multiply T1 by n to the power of minus A plus C. Again, I will stress the point that this is only applicable in motor movements. So it is not applicable where you think and contemplate before making a decision. It is not applicable where you do a motor movement and in the middle you stop to think and then continue on the motor movement. You have to be doing the motor movement from beginning to end in one shot. Now, is this useful? I would say yes, it's somewhat useful because it gives you a sense of how much improvement you can actually gain over time. So if T1 is taking you, say, 7 seconds, that's limiting because you will not get much faster. You will not drop because of the constants that exist here. You will not drop, say, 7 seconds, say, to 0.1 second. Okay, that's unlikely. But it will give you a sense of, as you keep repeating the movement, how much improvement you expect. Okay, so this is, for example, is very much applicable where you need to get a sense of the impact of using a specific piece of hardware. Okay, for example, let's say you have a joystick. I'm not sure if you have seen joysticks before. They used to be very popular in playing games, and I think they're still popular among gamers. So joystick is like a piece of stick. I think you must have seen it in the movie. So it's a piece of hardware. It almost looks like a gear shift for a car, and you can move it backward, in 360 degrees. Okay. So let's say you get this new joystick and you are experimenting with it because you would like to propose it as a game playing device. So people who play games, a certain game that you're thinking of, will use a joystick. And you have a choice between joystick and mouse, and you're concerned that it looks like moving joysticks are going to be slow. Now, you also have in mind certain movements you are interested that your players will do. For example, they would move the stick 360 degrees, almost like a circular motion with the joystick. Okay. Now, and you're wondering, is this going to be fast or slow? Because if they're playing the game and the device is slow, then everything will be slow. It's not going to be an entertaining experience. So what you do is you measure the amount of time it takes you to do this 360 degrees rotation for the first time. And you can try it with a number of people if you'd like, so just to get an average of, what is T1. And based on that, then you can come with an approximate, decision or a conclusion how fast this will ever get. If someone keeps playing like every day for hours and hours, in the 10,000 trial he's actually playing or attempt he's playing with the joystick, will he get faster? Then how much faster will he get? Okay. So if it turns out that the device is still very slow even after 10,000 times of usages, then you have to think your decision, should I actually add the joystick to my game or not? So here is my takeaway. The power law of practice can be used to find the approximate time to perform a mechanical task at the nth time. Okay, it has to be mechanical. Remember that. Let's come now to the big one. We have arrived to the big one of HCI. So the most famous law in HCI is called Fitts law. There are dozens and dozens of research papers and new interfaces built around Fitts law. And there are many, many experiments done on traditional interfaces as well, based on Fitts law. So let's see what this guy is. Now, first, the guy who made it, his name is Paul Fitts. He is a motor psychologist. He has nothing to do with computer science or HCI. He did this experiment for a reason. He wanted to know the limits of human motor movement. Why is that interesting? Because when you design any factory, any real factory, one of the concerns always is the safety of the labor. And in real factories, there are big machines, and the machines are designed to move as fast as possible to increase production. But there is a problem. If you make the machine move too fast, it might hurt one of the labor, because it's not made to be operated by humans, basically, if you make it way too fast than human capabilities. So this guy, Mr. or Dr. or Professor Paul Fitts, was interested in finding how fast can a human being move his hand from one location to another, because that's a task that is very common on assembly lines, where you have an assembly line, parts are moving, and the labor that are standing by the assembly line are either placing stuff or removing stuff from the assembly line. So he designed this experiment in which he asked participants to grab a pen that's connected to an electrical circuit, as the illustration appears, and the participant, would touch the dashed line and then move his hand to touch the other dashed line. The two dashed lines were connected to an electrical circuit, so when you touch, it records the time. When you touch the other line, the dashed circuit in the other line, it again records the time. And from that, he would know the time it takes to travel from one dashed line to another dashed line. What he also experimented with, or the variation he introduced in his experiment, he tried different inter-target distance. So he would make the two targets very far away from each other or very close to each other. What he also did, he changed the width of the target, which is the dashed line. So sometimes the width is very, very narrow, and sometimes it's quite wide. Okay? Now, why all of this is relevant to us, and why this is the most important law in HCI? Because actually, all what we do on traditional desktops, which are built on the metaphor of a physical desktop, is to move the cursor around, to position it on the top of an icon or a button, and then to click. So this movement, which starts from somewhere and ends on the top of an icon or a button, is actually just a one-to-one mapped to Paul Fitts' experiment. We start from somewhere and we go to a target, we land on the top of the target, and then we click the mouse. So for mouse-based interfaces, moving around, reaching to a target, and clicking is the only thing pretty much we do. There's nothing else. And so if we would like to get any interface faster, and this is really the most important, most common, most frequent task we do on a desktop interface. Move the mouse around and click. So if we'd like to get the interface faster, then we gotta speed up this specific interaction, because it's extremely common. In fact, it's like 90% of the time you're doing that, okay? And his finding became quite crucial, in the development of HCI, because all the ideas even you see nowadays, without realizing that, is influenced by the findings in his experiment. Okay, so this is what Mr. Paul Fitts is teaching us, that the time to reach to a target is dependent on two things: the reaction time and the movement time. This is what we described before as the discrete movements. We say that we move, we calculate the accuracy of our movement in terms of speed, or in terms of orientation, or in terms of displacement. We do a micro correction, which basically reorient ourselves a little bit, and then we move again. So there is reaction and there is movement, reaction and movement. This is not perhaps the most interesting part, because this is just a rewording of what I have described earlier. But what is really interesting is that he gave us this formula that is ridiculously applicable everywhere. People have tried to break this formula by showing cases where it doesn't work, and it never happens that it doesn't work. It always works. It's one of these amazing formulas. Now, in the formula, there are two variables, which is D and S. D is the distance to the center of the target from your starting point, and S is the width of the target. Now, A and B are constants that we are going to compute. But what he's basically saying us, and this is, by the way, is not generally an approximation. You would think of, that this is an approximation. This is not approximation. This is really dead accurate, okay? The time it takes to go from a starting point to a destination is a plus b log d divided by s plus 1. You'll get the exact time, okay? Now, again, this is universally applicable to all kinds of movements in all environments. So it has been reproduced using mices, using computer mices. It has been reproduced using joysticks. It has, and it still, holds the formula. It has been reproduced underwater. It has been reproduced using moving your legs. So you don't have to do the movement with your hand, even with your legs. And it has even been reproduced in outer space. So it's pretty, generic and universally accepted law of human movement. Okay. Now, the log d divided by s plus 1 is called the index of difficulty. Okay. This is really what determines the time for a specific device, because the A and B are going to be fixed for a specific device, but what will change is D and S. Okay. Now, A and B are device dependent, depending on what you're moving and with what you're moving. So if you're moving a mouse, it's different from moving a joystick, it's different from moving your legs. Okay. Now, A is the start and stop time of the device itself. Okay, any device, in order to move it, then it needs some time to actually get into the motion part. Okay, maybe because it has gears inside it, maybe because of friction, whatever. So that's the start and stop time of the device. That's the A. The B is the speed of the device, how fast you can actually move that device because of its nature. Because it has a weight, and the weight is being pulled by gravity downward, and if you try to move it horizontally, then you're working against gravity. So obviously a device that is very heavy and you're moving with to reach to a target, then the device itself will be slow because it's too heavy, while if it's light, then it's going to be a little bit faster in terms of its speed. Okay, so this is our infamous Fitts law. Now, how do you actually calculate the A and the B? This is what I have previously told you, but I am showing you constants in some of the laws like Hicks law, and I didn't tell you exactly how do you actually do it. So this is how you do it for Fitts law, and it's applicable anywhere else. Okay? What you're actually going to do for a specific device, you need to figure out the A and the B to be able to plug them into the formula. So what you're going to do is you're going to try out different values of D and S. Okay, you will vary the D, you will vary the distance to the target, and you will vary the S, the width of the target. And using the same device, it has to be the same device, you will measure what is the index of difficulty, log D divided by S plus 1, for different D's and S's. Okay, for every index of difficulty, you will get a different time. Okay, now what you do is you plot a line through the points that you have actually found. Okay, and then the intercept, the A, we said it's the start and stop time of the device. So that's the time that will elapse before you start actually the motion, and that will be the y-axis, because it's never going to be 0, because there is no perfectly free device that has 0 start and stop time. There has to be some friction, or there has to be certain pull from gravity, so it has to be a little bit above 0, at least some value above 0. Okay, so the intercept with the y-axis is going to be the start stop time of the device. Now the speed of the device is the slope. So I hope you can recognize that from your calculus day. The slope actually is telling you something about the performance of the curve you're looking at. Okay, and that will be the speed. The faster the device, the sharper the rise, and the slower the device, the flat the curve is. Okay, so again, just to reiterate how you calculate this, I will vary the D and the S. So I will pick, say, D10 and then S5, and then I will pick D7 and then S2, and so on. I change the D, I change the S, and I will calculate the time. Okay, but I'm calculating it not using A plus B, because I don't know A plus B, so there's no point in trying to calculate it from the formula. I will measure it. I mean, the time itself will be measured using a stopwatch or a timer or a piece of software. And for every log D slash S plus 1, I will find some time. So I will plot the index of difficulty against the time. Okay? Now, Fitts law still holds. So Fitts law, A and B should be represented in the figure in front of us, and they are. Again, the intersection with the y-axis is the time spent before the movement, which is the start time of the device, and we will assume the stop time of the device is the same as the start time of the device, and the slope is actually the speed of the device. Okay, so this is how we get these constants, by what's called, an empirical experiment or empirical calculations. Okay. Now, what's the implications of Fitts law? Why are HCIers always talking about Fitts law? What Fitts law is teaching us is that to speed up the interaction of what's called a target acquisition task, which means you move the mouse or you move your hand to touch something, or you move the mouse cursor to position it on the top of an icon to click on it. To speed up a target acquisition time, there are two things you can do, and they're pretty much that's all what you can do. Either you decrease the distance to the target, or you make the target bigger. And obviously the third case is you make both. Okay? You make both. So if you look at these four and I tell you, which is going to be faster to hit? Okay? Well, obviously the second one from the top looks like it's going to be faster because the target is big and the distance to the starting point is small. Okay? Now, if I tell you which one is going to be most likely the worst, and you're going to tell me it's D, because D is far away from the target. But when it comes to A and C, okay, so C is closer to the starting point, but it's small, while A is far away from the starting point, but it's big. And this is really showing the need for Fitts law, because I will calculate the distance to the center of A, figure out A's width, and plug that into Fitts law, and then I will calculate the distance from the starting point to C and figure out its width and plug that into Fitts law, and then I will know which one is actually faster to acquire. So the takeaway is that Fitts law will find you the time to reach to a target of width S, that is D distance away, using the constants A and B. And as I mentioned before, I cannot overstress the importance of Fitts law. So let's see some applications of Fitts law in HCI and why I'm putting all this stress on Fitts law. Here is one classical example of the utilization of Fitts law. And what you are accustomed to is the menu that appears on the left, which is called a linear menu. This is like when you open the file menu or the edit menu and so on. Now, let's employ our knowledge of Fitts law. What we know is that the menu always appears to the right bottom of the cursor. So when you click on File, you get this menu displayed below the word File, if this is the File menu. Now, the distance it takes to actually go to each one of the menu items, which I've replaced the menu items with just the day names, is different. The easiest one to acquire is today, but Saturday is the will require the longest amount of time, because you will have to travel down all the way till Saturday. Now let's rethink the design of the menu to make use of Fitts law, and what we will come up with is the menu on the right, which is called the pie menu. The pie menu will appear under the mouse cursor, where the cursor is in the center of the pie menu. The distance to travel to any one of the days is the same, and consequently it will take you an average the same amount of time to go and click on any one of the days. This pie menu design was suggested many years back. Even though it will beat any linear menu in any experiment, it has one problem which prevented companies from adopting it, companies like Microsoft and Apple making operating systems, which is that it's not really scalable, in the sense that if you have many menu items, you will end up overlaying one pie menu on the top of another pie menu, and then you will have to shift them a little bit towards the right, and you end up with a crowded scene with lots of overlapping pie menus. But if the number of menu items is small, they can be displayed in just using a single menu. Of course, pie menu is always better than a linear menu. And you actually see this type of menu, pie menu I mean, in computer games a lot, because game designers know about this pie menu and the fact that it's actually more efficient than linear menus. Here is another example. It's very classical actually application of Fitts law. If you've ever seen a Mac, or you do have a Mac, you know that there is a dock at the bottom of the screen, and as you approach to one of the icons gets bigger and it gets closer to your cursor. This is a direct application of Fitts law. When you are actually approaching a target, if we would like to speed up this type of interaction, we can do one of two things according to Fitts law, or do both. You make the target bigger or you make it closer, and in this case the dock actually is doing both. Once you approach an icon, it will get bigger and it will fly towards the cursor a little bit above, suspended in air, just like what is displayed here. And this is done to actually enhance what we call the target acquisition time, which means to decrease it, to be able to click on the icon faster. Here is another example of Fitts law application. Now, there are a number of researchers working on the enhancement to cursors. There is nothing preventing us from changing the cursor. The current cursor, which shows up in the Windows operating system and on the Mac operating system, is actually what's called a point or a tip cursor. Now, you have to move it and put it on the top of an icon to be able to click on an icon. Now, let's rethink the cursor and make it a circle instead of being the arrowhead that you often see on your desktop. Now, if we make it a circle, that would be really interesting, because any item within the circle perimeter, or within the body of the circle, which is highlighted here in blue or in light gray on the left, is a candidate for selection. So you don't actually have to travel all the way to a specific object, as long as the cursor, in this case a circle, has it inside its body. Then you click as if actually you positioned yourself, or the cursor, I mean the tip cursor or the arrow cursor that you have nowadays, as if you position it on the top of that icon and clicked. Okay, you will see in this video that I'm linking from this slide a variation of what's called circular cursors, or area cursors, a variation that shrinks and expands to encompass the closest object that appears on the screen. And this is very interesting. Again, we're doing all that to decrease the travel time, because I don't have now to go all the way to a specific icon to click on it. Once the circle has it in its perimeter, within its perimeter or within its area, then I can click the mouse as if actually I position it on the top of that icon. So again, this is an application of Fitts law. And you will see also in this research a number of cursors that have been proposed by researchers following the same way of thinking, that if we replace the typical cursor with an area cursor in the form of a circle, there's a number of interaction techniques that they propose, including, for example, I will just describe the one at the left, and I will leave the rest for you to watch in the video. The one on the left, once you approach a certain crowded area, I mean by crowded that there's a number of icons, using an area cursor, the icons will appear on the perimeter of some circle that appears with blue dashes along its body. And these actually objects that were close to you, perhaps were on the same line, but once you approach that line, they will spread around the perimeter of an outside circle outside to the area cursor, and then you can go and cross any one of them or click on any one of them. So actually they kind of fly and arrange themselves around your cursor. And there's a number of similar techniques discussed in the video. So don't expect in the future, that we will still have the same cursor we have nowadays. It will look a bit trivial, I know, for you if you haven't heard anything about HCI, you haven't studied HCI before. It's like, why care about cursors? Well, the issue is this is the most used user interface feature. So if we can speed it up, we will probably save you a few months from your life wasted on moving the cursor around. Okay, if you calculate the amount of time you're moving the cursor in a single day, and you multiply that by the number of days you will keep using the computer, obviously that's a lot of time. Okay, and if you add that up to all humans, then you're actually talking about even a much bigger number in terms of time. Now we're gonna show you. I'm gonna show you another application of Fitzlow, but in large displays. Now, large displays is something that will happen. You will see it in your lifetime. The existence of very huge displays in public places. Okay. Now, the problem with these huge displays, whether even not necessarily even huge, whether even they are medium size, like the size of an advertisement panel on the highway, on the ring road, for example. Now, these screens, the thing about them is that they are so big to the point that you cannot expect to use the standard user interface controls. For example, you don't expect to see a scroll bar on such screens, because if the knob of the scroll bar, if the knob of the scroll bar is way at the top, how would you go and touch it to be able to scroll down in a page or in an ad that is being displayed, or a content that is being displayed? I mean, it's unrealistic. You will need not just a ladder, you will need a very, very long ladder, probably like an ambulance ladder or a fire emergency ladder to be able to go all the way up to pull the scroll bar. So it's kind of ridiculous. So nobody is going to use it if it's so using a typical scroll bar. The interface elements we have on the desktop is suitable for the desktop, but once you scale up to the size we're talking about here, nothing really works effectively or efficiently. So the thing is, with the dropping in the cost of the hardware, it's not anymore science fiction to talk about the displays that are 72 inch or 100 inch or 150 inches. Okay. And obviously these will be deployed mostly in public places, but even in public places there are need for certain kinds of interactions. So we will see later on what I describe as basic input tasks that you should support, at least partially, in a user interface. Now, one issue is, how would you reach to distant targets? So I'm going to show you a research work actually that, again, built on Fitzlow, try to facilitate the use of touch screens to enable the navigation and acquisition of very distant targets. Okay, so before we move on to that work, let's basically summarize the issues in front of us here. First of all, we have no idea how to input into a display of of a large size that is placed in a public space, because you don't expect to see keyboards around. Okay, for example, with the current COVID-19 situation, any piece of hardware that will be exchanged by people, where that will see an exchange of hands, might be a source of infection. So you don't want keyboards, you don't want mouses. Okay, so we have a problem in the input. Okay, we also have a problem in reachability. If the screen is too big, if it's like 6-7 meters high, how would you go and touch something that's at the top of the screen? Okay, we also have an issue of privacy in large displays. If I would like to see a message that is personal on a public display, assuming that is possible, or someone would like to display a message to me that is personal, it doesn't have to be extremely personal. It might be just like some personal information. For example, I get a message from one of the shops that knows about my presence in the mall, and it's going to display to me a message telling me that we can offer you this package if you buy from us, so and so. Okay, Perhaps there's a lot of invasion of privacy if if it reaches to this level, but it's actually reaching to that level in certain countries in the world. There are no laws that protects privacy, including the privacy of location. And this is, for example, happening in Egypt. Every time I go to Carrefour, I get a message afterwards telling me about the discounts in Carrefour. Which means that they track my cell phone and they know now that I'm in Carrefour, and they bombard me with messages. Okay, so basically, for these three problems, we need a lot of new interaction techniques that doesn't exist, and new hardware as well that doesn't exist. Okay, and this is a topic of research. So this is the work I was referring to. I would like you, to see the video to understand it completely, but the idea is quite simple. If the big display has touch facility, so I can touch it, and the screen detects my touch, what Anastasia proposes here, the researcher, is the following. It proposes what's called the bullseye menu, which is a menu that appears when you touch the screen. And as you move towards one of the targets that you would like to acquire, the targets that are far away will fly to you and become very close to you, close to where your hand is, and will be displayed in small size. Okay? So this will enable you to select something that's far away, like 7 meters up away from you. The target itself will fly and come close to your hand, and then you can go and click on it or swipe on it to actually do the selection. And you can see the video, there are more details related to that. So the takeaway, okay, this is a very important one. To decrease target acquisition time, either you decrease the distance to the target or increase the width of the target, or both. And this is basically what we get from Fitts law. We will talk now about steering law, which is an extension of Fitts law. Now, Fitts law generally covers movement in one direction or in one dimension from a starting point to an end point. What if your movement, you start and then you don't stop? You keep going through what we can imagine as a tunnel, steering through the tunnel until you find a point where you exit the tunnel or you change direction to go to another tunnel that is connected to the first tunnel, and from the second tunnel you go to a third tunnel, and so on. Okay, this is a very common movement actually you do with the mouse, which is to steer through the menus as it's displayed here. So for example, if I would like to click on use all, I will take the mouse from its location to click on format. If I would like to evaluate the performance of that, I'll be using Fitts law, because this is one-dimensional movement from a starting point to the format menu item. Now, when I click on the format menu, okay, the one at the top, I get this menu opened, and I know that I would like to click on use all. So I will go and I will steer with my mouse through the font line, going downward to the ligature menu item, and then going towards the right, and then going towards the bottom until I go to use all. Okay, this movement, we call it a steering movement. Okay, it's not a typical Fitts law because it goes in 2 dimensions, and it involves crossing multiple targets one at a time along the way. Okay, the target for me in the first phase was at the end of the font, where you see the arrowhead that is highlighted in white, and it's covered by the dots, and that's a target I had to cross to be able to open the next menu. And then there is another one that appears at the second line from the bottom in the second sub menu, with again a white arrow, and there is another target there which I have to cross to go to use all. Okay, now this kind of movement, which is very common by the way in playing games, that you steer through a path, you could evaluate or find out how much time it's going to take the user to do it, and in a very accurate way using steering law. So steering law is derived from Fitts law. So when you look at it, you see the formulation on the left. You shouldn't be surprised that we are saying log d divided by w plus 1, which means it's the index of difficulty. In fact, what steering law is, it's the index of difficulty multiplied by the number of tunnels that you're going to go through. And the number of tunnels is related to the number of goals, because one tunnel will have a goal at the beginning and a goal at the end, and consequently it's always the case that the number of goals is the number of tunnels plus 1. So you multiply the number of tunnels by the index of difficulty, and that will give you an approximation to the amount of time it's going to take the user to steer through those tunnels. Okay, so the general formulation appears at the bottom. It's n for number of tunnels multiplied by log d divided by n by w plus 1. So it's very similar to Fitts law, except we have incorporated the number of tunnels in our calculations. Takeaway is that steering law finds the time to navigate through a path of n tunnels. N multiplied by log d divided by n by w, and n multiplied by w plus 1. So let's put all the pieces we have learned up to now in terms of time, reaction time to any user interface change. So the model human processor has divided the reaction to a perceptual part, a cognitive part, and then a motor part. We know that the perceptual processor has a cycle time of 100 milliseconds, the cognitive processor on average is 70 milliseconds, and the motor processor on average is 70 milliseconds. What those amounts to or add up to 240 milliseconds. What does that mean? Okay, it actually means a lot, way beyond HCI. What it means is anything happens in 240 milliseconds for the user is not able to react to it. Okay, the user is busy through during 240 milliseconds after any change in the user interface trying to react to that change. So in other words, trying to make computers or software run faster has a limit, which is the human reaction to it. Okay, because if your concern is that you don't want to slow the user while interacting with software, well, the human or the user himself is slowed down by his processing of the output displayed to him, and he's slowed down every time by 240 milliseconds. What that really boils to is that you have a gap of 240 milliseconds to do any computation, okay, until he responds back to you. Okay, and this is really the subtle message here. We have a limit on how fast we can respond to things, and that is this number. So a human response to an interface stimulus cannot be faster than 240 milliseconds. So don't expect from the user an input before 240 milliseconds. We will move on to the last part in the motor system, which is the muscles and how the muscles move. Now, remember the Minority Report movie I told you about in the first lecture, that it was a sensation when it was released because of the user interface that was displayed in that movie, which is quite futuristic from many people's perspective. By the way, the gloves that Tom Cruise is wearing here, you can buy them now from Souq for like 40 pounds or something. So if you get interested in the gloves, you can buy them, and they have nothing to do with computers. They're just regular gloves with LEDs embedded in them. Anyway, so I'm teaching you this because it's a trend now to actually make movies again with lots of really bad designed interactions, and you really need to understand how the muscles move to be able to build correct interactions, especially for new devices, which is becoming easier and easier. And as I mentioned before, you can propose a new device in the project of the course, and you can propose interaction techniques, including gestures, but I want you to keep in mind what we're going to discuss today so that you don't do something like what Tom Cruise did in Minority Report. So let's start by studying the muscles. So here is our body. What you see here is an anatomical chart of the human muscle system. We have 642 muscles. They are layered on the top of each other, almost like an onion. That's how it's often described in medical textbooks. Okay, and what is important for me to understand, what's important for me that you understand, that's the first thing, is that the muscles are attached to our bones using tendons. Okay, and these tendons is what gives us elasticity, and that's why you can move your body parts in all kind of movements with fine resolution, or at least with good resolution. Okay, so I don't really worry here for you to and I don't want you to memorize the names of all of these muscles, but I want you to look at them, and I want you to notice something, that there are some big muscles and there are small muscles. Okay, this should be intuitive already to you, but this is the first thing you need to observe, because this is the first or the second thing we're going to talk about. Now, the first thing actually we're going to talk about is the role of tendons. Okay, now again, tendons attach your muscle to your bone. Tendons are elastic. what they give you is something called the range of motion. For every muscle in your body, there is a safe range of motion. If you cross that range of motion, you are exposing yourself to injury. Okay? So, if you're going to design gestures for a system where the user moves his hands or arms or shoulders or legs, you have to understand the range of motion for every muscle you're using. And you have to make the motion and teach the user the motion so that he's always within the correct or the safe range of motion. This is also, by the way, very applicable if you go to a gym and exercise with weights. If you've ever seen a trainer or you trained under a trainer, a weight trainer, they would tell you that there is a certain posture or a certain angle by which you raise or lift the weight. Otherwise, you're going to damage your tendons and consequently your bones. So that is related to the range of motion. Now, in any anatomical textbook, they will tell you, okay, what's the range of motion for each one of the muscles in your body? Okay, some of the muscles are quite embedded, so they don't actually cannot be moved alone. They are part of a group of muscles because, as I'm saying here earlier, the muscles are layered. Okay, but at least for HCI purposes, most of the muscles we will be interested in have a specific known range of motion. Okay, and the range of motion will be expressed as angles, say from 30 degrees to 110 degrees. So that's the first thing you need to remember. Now, the second thing you need to remember, I was just referring to that in the previous slide, we have generally two major classes of muscles in our body. We have very small muscles and very big muscles. The largest muscle in your body is the glute, which extends from the lower back all the way down to your knee. Now, this is why actually when you go to the gym and if you'd like to lose weight, the coach will tell you exercise your core, because when you exercise your core is actually extending from the middle of your body and downward. That area has lots of big muscles, and big muscles consume lots of energy because they are big by definition. Now, on the other side, we have another set of muscles that are generally referred to as small muscles, and these muscles, as the name implies, they're very small in size. And the area that we are always interested in SCI is the hand muscles. There's lots and lots of muscles there. There's about 40 of them layered on top of each other. Now, by design, small muscles are made for fine movement, and large muscles are made for coarse movement. Coarse means not fine. So if I ask you, can you move your feet 0.2 centimeters? You will not be able to do it. You will not be accurate in doing it. You will probably overshoot and move it few centimeters, while I'm asking you to move it 0.2 centimeters. On the other hand, a small muscle, if I ask you to do a very small movement, it is made for such fine movements. So if I tell you move your finger 0.2 centimeters, after a while you will be able to do that. You will know, what is that, okay, and how you can actually do such a movement. So again, the rule is small muscles means fine control movement, large muscles means coarse movement. Okay. Now, this has implications for SCI design. If you design an interface, for example, for a laborer who is standing in a factory, and since his hands are going to be busy with the assembly line, then you're going to design buttons that are placed on the floor, and he will click on a button, say, to control a device, a digital device or a digitized device, or a digitally controlled device, by pressing on them using his feet or her feet. Now, we said large muscles are good for coarse movement. So coarse movement means no fine resolution. What that means is when you actually design the button, you gotta get a really big button, probably the size of half an A4 paper, because that's what we could move with our feet, big distances. Okay, so you cannot make a button like an icon, little icon, 16 pixels by 16 pixels. You have to make it, so big that it's suitable to be hit by the foot. Okay, so what is the interface you designed for big muscles? is different from the interface you designed for small muscles. That's the takeaway here. Now, I would like to connect the notion of small muscles with the area in the brain that control these muscles. Okay, there is actually a connection. You see, the more the finer the movement that you make with your small muscles, the more control you need to exercise on the muscles. The more control you need to exercise on the muscles, the more nerve fibers that are going to the muscles. The more nerve fibers that are going to the muscles, the more the signals coming to that muscle from the brain. That's why if you look in the motor cortex that we've described earlier, and you look at the fingers area, you will see that it's actually quite big compared to, say, your elbow. Because, you know, you move your hand with a very fine, what we call dexterity, or ability to do fine resolution movement, compared to your elbow. How many ways you can move your elbow or your shoulder or your trunk or your hip or your knee? Okay, it's very limited. Okay, it's just basic movement, forward and backward kind of thing. Okay, but you cannot, for example, rotate your hip or your knee separately from the rest of your body. Okay, and you cannot move it in an angle, in an XYZ direction. Okay, in a 3D. It's because it's tied to what's above it and what's below it. So the movement is limited, and consequently, you don't need lots of nerves to control it. While when we talk about the hand, well, the story completely changes. You know, you have 40 muscles layered on top of each other that are together capable of doing very fine movements. And by the way, we are the only creatures on earth who do the kind of movements that we do with our hands. Okay, we do some really crazy stuff with our hands, the way that we rotate things, or we control a knob, or we hold something that is very fine, like a hair thread, with our 2 fingers. Okay, so all these very fine movements, all other creatures on earth, including monkeys and chimpanzees and so on, or gorillas, are not able to do it with this kind of dexterity. Now, so it is actually related to a lot to your motor cortex. What you can do with a specific muscle. Now let's come to the very important topic of the amount of work you need to do any kind of action. Now, if you look at this chart in front of you, and I tell you, what are you carrying here? You will tell me, oh, I'm carrying the ball. And that's not entirely correct. This is an incomplete answer. What you are actually carrying is the weight of the ball and the weight of your forearm. Who is carrying your forearm? It's actually your biceps, which is connected to your shoulders. So ultimately it's your shoulders, carrying your arm. So if you would like to think of the total weight that is being carried by your shoulders, it's the weight of the ball plus the weight of your arm. Okay, otherwise your arm would have fallen to the ground. Who's preventing it from falling to the ground? It's actually it is tied to something, and that something is actually carrying it, and that's why it's not falling down. Okay, so this has an implication. We are working always against gravity. What that means is, the bigger the muscle, the more work you do. And the more work you do, the more tiring you will become. And the more difficult you will actually be, facing in actually doing a specific movement. Okay? So don't just think of what you are moving with, think of the organ that is doing the movement. Okay? So here are a number of takeaways. Small muscles can be used to do fine movement. Okay? For example, moving a mouse few centimeters to control the mouse cursor. Okay? The opposite is going to be tiring to the small muscle. Moving small muscles large distances should be avoided. Okay? Now, why would you need to move a small muscle a large distance? If you design an interface where the user is using the small muscle to travel a long distance, okay, you will get the small muscle tired. In fact, the mouse is considered the most successful user interface device because it fits perfectly with the muscle that is moving it. First of all, you control the mouse with your hand. So there is the weight of your hand and there is the weight of the mouse. But the mouse is mounted on the table, so the table is carrying the mouse. You're not carrying the mouse. And your hand also rests on the table. What that means is you're not really carrying your hand. You will be carrying it against gravity if you raise it up and suspend it in air. But if you rest it on the table, now the table is carrying your hand. The movement that you do with the mouse is very limited. You can traverse even the biggest screen that you would imagine sitting in front of by moving few centimeters on the table. By moving the mouse, I mean few centimeters on the table, which means that you're moving small muscles, small distances, which is perfect, okay? And the other perfect thing is you're not carrying anything, okay? The table is carrying the mouse for you, and it's also carrying your hand. Now, the big muscles, this is the second takeaway here, the big muscles can be used to do chorus movement, okay? Big muscles is for chorus movement. Now, moving large muscles, small distances, should be avoided because the user will not be able to perform the small distances. It's not about getting tired as much as it is not actually achievable, okay? And I already discussed the example of the assembly line and how big you should make actually a button that the user click with his feet. Now, the third guideline here is that working against gravity affects the performance, okay? So let's go back to Mr. Tom Cruise. In the movie, if you watch a clip from it on YouTube, or if you get the movie and watch it for that purpose, you will notice that throughout using the interface, he's raising up his hands. His hands, not just his hands, actually his two arms. His two arms are connected to his shoulders, which is connected to his back. Okay, so now the weight of his arms are falling on his shoulders, which is supported by his back muscles. And you can do that as an interaction, provided that you do it for a very short duration and basically infrequently. And when you do it in terms of number of times, it's going to be infrequent, and in each one of those times is going to be for a very short duration. Okay, so intermittent interaction. But what you see in the movie, throughout the movie for like an hour or more, maybe perhaps an hour and a half, you see him throughout the movie working with the interface, and that's the norm basically. Like if you would like to work with that interface you have to raise your two arms up and hold them against gravity. Okay? Now, here is what's actually going to happen if you do that. First of all, you'll get the user tired. And this way, if you design such an interface, you probably need like someone who is a bodybuilder to be able to use your interface, because anyone else will actually get tired within 10 to 15 minutes. That's number one. Number two, once they get tired, they will not be able to position their arms in space in the right location to control the interface. So that will lead to an increase in error rate. Okay? So instead of clicking on a specific button or touching a specific icon, they will touch the one beside it, or the one below it, or the one to its left, or the one above it. Okay? So there will be overshooting and undershooting in the performance because of the tiredness. And you don't want to reach with the user to the point that he's tired from using your interface, and consequently he starts making errors. Okay? So the general rule is don't design repetitive actions with big muscles. You can do it once in a while, but don't do it continuously. Don't make it the norm in the interface to work with big muscles all the time, raising them against gravity. Now, the next guideline we're going to look at is the following, that you should avoid repetitive movement, okay? Because repetitive movement will cause exhaustion to the muscles. Now, if the muscle is exhausted, what that means is you will not be able to control it. In fact, you could keep using a muscle to the point that the nerve gets saturated. Now, what do I mean by saturated? Here is how the instruction is sent from the brain. It's an electrical signal that travels from the brain through your spinal cord, the nerve, which is part of the central nervous system, to the muscle to move it, to contract it or relax it. Now, if you keep doing that for a lot of time, in order for the electrical current to travel, there has to be potential difference. If you keep sending the same signal over and over again because you're doing the same movement over and over again, ultimately there will be no potential difference along the wire that connects from your brain to the central nervous system, or basically the spinal cord, because you could think of it as a wire, as an electrical wire that goes from your brain through your spinal cord all the way to the muscle. Now this wire will get saturated with electrons, and once it gets saturated there will be no current able to flow because there is no potential difference. Okay? Actually, you most likely you have experienced this. This is what we call in Arabic when someone has this feeling in his leg or his arm, tanmil. Okay, tanmil is the saturation of the ions in the nerve, so you can't really move it. And it happens. It could also happen if you actually do a repetitive movement. The more you do the repetitive movement, suddenly you're not able to control the movement, okay, and suddenly you're not able to control your muscles. It's not obeying you, okay. That's the saturation, and obviously you will immediately get an increase in the error rate if you do that, okay. So what this tells you is that when you design a set of gestures to interact with a system, is that you should separate it by time lapses where you're not doing the gesture, okay. And by the way, for your information, the status of computer vision has advanced to the point that there is nothing preventing a company like Microsoft or Google to design an interface that is completely made up or supported by using gestures. So for example, if you're working with Windows and you would like to shut down the machine, you would wave bye-bye so the machine shuts down, okay. Or if you would like to close a window, you would do a certain gesture with your hand to close the window instead of clicking on the X at the top right, okay. In terms of being able to do that, it is doable nowadays with the advancement in computer vision. But companies like Microsoft and Google are very reluctant from doing that because they know there are problems associated with gestures, with performing actions by waving in air or moving the hand in a certain way, and that there will be trouble, while doing these actions for extended periods, and users will not understand why it is the case, okay. So they would blame the company at the end, and that is why they are refraining from integrating more gestures into the operating system or generally into their software. Now, the fifth guideline is that rotational movement requires fine dexterity and lots of muscles working together, so you should generally avoid it, or when you do it with lots of caution and separated by other gestures that are not actually requiring rotational movement. I mean by rotational movement, imagine holding a ball in your hand and you keep rotating the ball by moving your fingers around, okay? You're not moving in space, you're standing still in space with your hand, but it is actually rotating the ball itself within using your 5 fingers, okay? So this is the rotational movement I'm referring to here, and this is one of the most complex movements, and only us humans are able of doing it, but it actually requires moving all the 40 muscles together to be able to do such rotational movement, and it should be avoided because it just makes the user hand tired faster than anything else, okay? And you can actually try it out. Get a tennis ball, put it in your hand, and try to rotate it for a while, and immediately you will start to feel the pain from doing that. So I have put here a list of questions that you need to ask yourself while designing a gesture, and I'm going to leave the questions for you. They are available in the lecture slides. They all rotate around the topics I have been discussing up till now and these guidelines. It's just they are now in the form of questions, like a checklist. If you're doing a project that has some hardware component and you're going to design gestures for it, this is what you need to check to make sure that your gesture choices are correct. And this is the second part of these questions. So let's go through the takeaways. Small muscles are good for fine movement. Big muscles are for coarse movement. Second one, gesture-based interfaces are best suited to short duration interactions, else muscles are tired from carrying the weight, decreasing accuracy of movement, and consequently more errors. Next takeaway, using a muscle to do the same action for an extended period of time will lead to nerve saturation, which is the inability to control the muscle. Now, let me show you a bit of HCI research around the use of muscles, okay? Now, first of all, I would like to prove to you that muscles are controlled by electrical signal. An electrical signal is made up of ions that are free to move, and ions are free to move because we have a potential difference in the media. So I've linked here for you a little bit of a gross video, but it's somewhat entertaining to watch. It's frog legs just immediately after the frogs were slaughtered. And by the way, in France they eat frogs. It's not a big deal there apparently. I'm not sure if the movie is actually from there or not, but there are people who are eating frogs nowadays. Anyway, so here's what happens. This guy who appears in the video will actually put some salt on the frog legs, and once the salt is absorbed by the skin, the legs will start to move. Why? Because salt, which is, if you remember from your old good old chemistry days, is sodium chloride, Na plus Cl minus. So the minus is a free moving ion, and this is just like the free moving ions that will exist on the central nervous system coming from the brain. So the muscles are tricked because they are designed to respond to these free moving ions. The muscles are tricked and they start playing around, as you will see in the video. All this because of the sudden creation of a potential difference in the skin or in the body of the muscle itself. Okay, so convince yourself that muscle movement is all about electrical current. Okay, now the thing I would like also to tell you is that when a muscle starts to move, it vibrates because remember it's attached to tendons, and the tendons are attached to the bones. So the tendons are very flexible, and when a muscle contracts and relaxes, the tendons also would vibrate, and that becomes the source of vibration, the movement of the tendons along with the muscles. Okay, those vibrations could be captured, and every muscle movement has a unique vibration signature, if you like. Okay, so we could capture the vibration of the muscle. I know it sounds a little bit science fiction, but it's not really. I mean, you will see some videos related to that. Muscles basically produce vibrations when they move because they are attached to tendons, and we can record the whole thing. And because every muscle movement is made with a certain intention, and it's made with a certain velocity, and it's made with a certain amplitude, the vibrations are going to be slightly different. But the stages of machine learning has advanced to the point that we can differentiate between those vibrations. So let me show you. This is not science fiction what I'm going to describe. You will see the video actually. I've linked it to you here because it's not available on YouTube. This is the research video by somewhere in I believe in Germany, and this is how this works. Okay, now remember I just told you when a muscle moves it produces vibrations. What if we record the vibrations and then replay it in someone's hand at the right location? Wouldn't the muscle move the same movement? And the answer is yes. Okay, if you capture the vibration, which is the result of the movement, and then you go to a stationary muscle and you reproduce the same vibration, the muscle will make the same movement. Okay, I'm not going to go into the technical details here because what I'm saying is a bit shallow, but I will just keep it at that level. The point is I could induce movement in a muscle by vibrating it. Okay, now this research is very innovative because here is what is going on. The user will hold a pen and will start drawing, and he doesn't know how to draw basically well enough. He starts drawing a naive drawing, and then he will put some marks on the paper, as you will see on the video, and his arm has electrodes attached to them, just like the electrodes we have seen before to record from the brain signal. But these electrodes are not capturing the vibration, they are actually playing vibrations. We are sending a vibration through them. And the vibrations are very well controlled because it starts to move the hand in a specific way so that we control his hand while he's drawing, or we force him to draw what we want. Now, who's forcing him? It's the software will force him to draw a correct engineering drawing that represents, for example, the flow of air around this car. So him alone will not be able to actually simulate the aerodynamics correctly, because his hand and his brain is not capable of doing the computation on the fly and just using a simple pen like this capture the result of sending air through the body of the car and what will happen to the air as it travels on this body of the car. He might be able to produce the same output that we will see or you will see in the video, but then he would have to use an engineering drawing program like AutoCAD or whatever to actually do it properly. But now, if we can control his arm, we will do it for him. We will just use his arm as an output device. Instead of using a printer, we will use his arm to actually output the correct drawing. Okay, it's quite an entertaining piece of video to watch, with showing what we can do with capturing vibrations and replaying vibrations, or replaying a modified version to be more accurate of the vibrations to control the muscle directly. Now here is another video. I would also like you to see it. Here is like the two sides of the story. You have this lady who will make an action, and then we will capture the vibration or the electrical signal, if you'd like to be more accurate, and then we will replay that in the guy's arm. So she will move her arm, and he will involuntarily move his arm, doing the same movement she is doing. Okay, so he has no control anymore on his arm. She is controlling his arm, or the system is basically controlling his arm by capturing the signal from what she is doing and replaying it in his arm. Okay. Now I am mixing here the words vibration and the signal. I don't want to go into the details, but you could think of them as being one or the other, and obviously there are differences, but I will not really dive into the details here, because this is beyond the scope of this course. There is another course I'm teaching, which is brain-computer interfaces, where I cover that in more detail. This is even more interesting, more of science fiction stuff here. Microsoft developed this device that captures the movement of your jaw and your even extends all the way till the esophagus. So you could basically whisper or even move your mouth with a certain word without really producing a sound that is audible by anyone who's close to you, and it will detect what you're trying to say. Okay, this works on a limited set of words, because it involves machine learning and training and so on. But the idea is, you're not saying it, but you're saying it. You're saying it internally, if you'd like, and the device captures the vibration and will know what word you actually intend to do. So this is another example of working with vibrations. This is another one as well, but it's kind of the reverse of what we have seen before. Here we capture the signal from the arm, and we enable the user to do certain actions based on the capture signal. So we have seen before works where we put these electrodes on the brain to know the intended motion. Okay, while over here actually we are capturing the intended motion in action, and we play with it in the interface as you will see in this video.